Hello there, and welcome to Deep Sleep Seas. I'm so glad you found your way here tonight. Maybe the day felt long, or perhaps you're the kind of person who likes drifting off to the rhythm of waves and the whisper of ocean mysteries rather than counting sheep. Either way, this evening's journey is meant for you. You have nothing to do but rest. Let your muscles soften, your breathing deepen, and your thoughts grow light, as if you're floating on gentle swells. Because tonight we're exploring something extraordinary yet invisible, ancient yet ongoing, quiet yet powerful beyond measure. We're diving into the story of upwelling, the ocean's ancient cycle of renewal, a hidden engine that has shaped life in the sea for millions of years, bringing treasure from the darkness below, sustaining entire ecosystems, feeding billions, and connecting the deep past to the living present in ways we're only beginning to understand. You'll hear tonight of cold water rising, of blooms that paint the ocean in brilliant colors, of fisheries that feed the world, and of cycles disrupted and renewed. Some of what you hear may surprise you or perhaps simply guide you gently into sleep. But before we begin, if you find these ocean stories soothing, consider subscribing so you don't miss the next voyage into the blue. And if you're still awake enough, let me know where in the world you're listening from. I read every single one. Now, let's begin. The ocean surface appears calm from shore, a vast expanse of blue or gray stretching to the horizon, seemingly uniform, unchanging. But beneath that deceptive stillness lies constant motion, currents flowing like rivers through water, temperatures shifting by degrees, layers of different densities stacked upon one another like a liquid layer cake. And in certain places, under certain conditions, something remarkable happens. Cold water from the deep, water that has been dark and still for months or years, begins to rise. Slowly at first, then with increasing momentum, it climbs upward through hundreds of feet, sometimes thousands, carrying with it treasures that transform the ocean above. This is upwelling. Not a dramatic event you can watch from the beach, not a wave or a storm, but a fundamental process as old as the oceans themselves, a quiet miracle of physics and biology intertwined. When winds blow across the ocean's surface in just the right direction, when the Earth's rotation adds its invisible twist, when coastlines angle properly to receive what the deep has to offer, cold water wells up to replace the sun-warmed surface water that has been pushed aside. And when this cold water arrives in the sunlit zone, it brings life with it. Not life in the sense of living creatures swimming upward, but life in the form of nutrients, chemical compounds that have accumulated in the darkness, waiting. Nitrogen in the form of nitrates, phosphorus as phosphates, silicic acid for building tiny glass shells. These are the building blocks that the surface ocean desperately needs but rarely has in abundance. The warm, sun-drenched surface waters have usually been picked clean of nutrients by countless microscopic organisms over time, leaving them beautiful but relatively barren. But when upwelling brings nutrient-rich deep water to the surface, it's as if someone has poured fertilizer onto a garden. Within days, sometimes hours, the water responds. Microscopic plants called phytoplankton, drifting throughout the sunlit zone, suddenly find themselves in paradise. Sunlight from above, nutrients from below, and all the carbon dioxide dissolved in seawater that they could possibly need. They begin to multiply with extraordinary speed, doubling, then doubling again and again until their numbers reach into the billions per gallon of water. The ocean, which may have appeared relatively clear, begins to change color. Patches of green or brown or even milky turquoise spread across the surface, visible from satellites in space. These are phytoplankton blooms, and they form the foundation for some of the richest ecosystems on Earth. Upwelling zones occupy only about 1% of the ocean's total surface area, a thin band along certain coastlines, strips of productivity in a vast blue desert. And yet these narrow zones account for roughly half of the world's total marine fish production, half, from 1% of the ocean. The mathematics alone is staggering, but the reality is even more remarkable when you consider what this means. The major fisheries of the world, the ones that feed millions of people, the ones that drive coastal economies and sustain entire cultures, are almost all found in upwelling zones. The cold, nutrient-rich waters off the coast of Peru and Chile, the California coast, the waters along Namibia and South Africa, the regions off Northwest Africa, the seasonal upwelling zones off Somalia and Oman during monsoon season. These are the ocean's breadbaskets, The places where the invisible machinery of upwelling creates such abundance that humans have built entire industries around harvesting it. But this abundance isn't automatic or guaranteed. It depends on winds that must blow in the right direction with the right strength, on ocean currents that must flow in their established patterns, on the earth continuing to spin as it always has. When any part of this delicate machinery falters, as it does during El Niño events, the consequences ripple outward through ecosystems and economies alike. Fish populations crash, birds starve, coastal communities face hardship. The absence of upwelling reveals just how dependent we are on this ancient cycle, how much life hangs in the balance of cold water rising. Tonight we'll travel through this hidden world, exploring how upwelling works, where it happens, what it brings from the depths, and why it matters so profoundly. We'll venture into the mechanics of wind and water, into the chemistry of nutrients and the biology of blooms, into the history written in ancient sediments and the uncertain future shaped by changing climate. And through it all you can simply rest, letting the story wash over you like gentle waves, carrying you towards sleep on the rhythm of the ocean's oldest gift. To understand upwelling, we must first understand something strange about the way water moves in the ocean. When wind blows across the water's surface, you might assume the water moves in the same direction as the wind, and it does, at first. But then something curious happens, something that seems to defy common sense until you remember that the earth beneath the ocean is spinning. The Coriolis effect, named after a 19th century French mathematician who described it, is a consequence of our planet's rotation. Objects moving across the Earth's surface, whether air masses, ocean currents, or even projectiles, appear to curve to the right in the northern hemisphere and to the left in the southern hemisphere. This isn't because some force is actively pushing them sideways, it's because the Earth beneath them is rotating, and different latitudes rotate at different speeds. The equator moves faster than the poles, completing the same rotation in the same 24 hours despite having much more distance to cover. This differential rotation creates the apparent deflection we call the Coriolis effect. In the ocean, this effect becomes beautifully visible through a process called Ekman transport, named after Vagn Walfrid Ekman, a Swedish oceanographer who worked it all out in the early 20th century. When wind blows steadily across the ocean surface, it drags the top layer of water along with it. But that top layer doesn't move directly with the wind. The Coriolis effect deflects it to the right in the northern hemisphere, to the left in the southern. And then that deflected layer drags the layer below it, which also gets deflected, but even more, creating a spiral pattern of water movement that twists deeper and deeper into the ocean, each layer moving at a slightly different angle and speed than the one above. This spiral is called the Ekman spiral, and the net result of all these layers moving at different angles is that water, on average, moves perpendicular to the wind direction, 90 degrees to the right in the northern hemisphere, 90 degrees to the left in the southern. This seems impossible at first, wind blowing one way, water moving at right angles to it, but it's been confirmed countless times through observation and measurement. Now imagine wind blowing parallel to a coastline, flowing steadily along the shore. In the northern hemisphere, if the wind is blowing southward along a western coast, like the coast of California, the Ekman transport pushes surface water offshore, to the right of the wind, away from the land. The water near the coast gets pushed seaward, creating a deficit, an absence that must be filled. Nature abhors a vacuum, even in liquids, and so water from below rises to take the place of the surface water that has been pushed away. This rising water is upwelling. It comes from depths of 100 to 300 feet, typically, sometimes deeper, drawn upward by the absence above. And because this water comes from below the sun-warmed surface layer, below the thermocline where temperature drops sharply, it arrives cold. Much colder than the surface water it's replacing. When you visit an upwelling coast on a summer day, you often encounter a paradox. The air may be warm, even hot, but the ocean water is shockingly cold. A beach in Peru, located in the tropics, may have water temperatures around 16 degrees Celsius, cold enough to make swimming uncomfortable without a wetsuit. This coldness is upwelling's signature, the proof that deep water has been brought to the surface. Satellite images that measure sea surface temperature reveal upwelling zones as dark blue or green streaks along coastlines, fingers of cold water extending into warmer offshore regions. The temperature difference can be dramatic, sometimes 8 or 10 degrees Celsius colder than the surrounding water, a sharp boundary between worlds. But temperature is only part of the story. The real treasure carried by upwelling water is invisible to satellites and to human eyes. It's chemical, molecular, the accumulated wealth of death and decay transformed into the building blocks of life. In the deep ocean, below the reach of sunlight, organisms that die in the surface waters sink slowly downward. This is called marine snow, a constant gentle fall of organic particles, dead phytoplankton, fecal pellets from zooplankton, fragments of larger animals, bits of everything that once lived in the sunlit zone. As these particles sink, bacteria and other decomposers break them down, consuming the organic matter and releasing inorganic nutrients back into the water. Nitrogen, originally incorporated into proteins and DNA, is released as nitrate. Phosphorus from ATP and other molecules becomes phosphate. Silica from the glassy shells of diatoms dissolves back into solution as silic acid. These nutrients accumulate in deep water because there's nothing down there that can use them. No phytoplankton to absorb them, no sunlight to power photosynthesis. They simply build up over time, waiting. The deep ocean becomes a vast reservoir of nutrients, rich beyond measure but utterly dark and cold and still. Scientists call this the biological pump, this vertical movement of nutrients from surface to depth through the sinking of organic matter, and from depth back to surface through upwelling and mixing. Without this pump, without upwelling to bring nutrients back up, the surface ocean would eventually become depleted, a desert of blue clarity where nothing can grow. Upwelling completes the cycle, returning what sank, giving death another chance at life. The rate at which upwelling occurs varies enormously. During weak wind conditions, water may rise at only a few meters per day, a gentle, almost imperceptible lift. During strong upwelling events, when winds blow hard and steady for days or weeks, water can rise 10 meters per day or more, a relatively rapid ascent that quickly floods the surface with nutrients. The upwelling season in many regions is tied to the seasonal wind patterns. Off the coast of Oregon and Washington, upwelling is strongest in spring and summer when northwest winds blow consistently. During winter, winds shift, storms arrive and upwelling weakens or ceases entirely. This creates a seasonal pulse in the ecosystem, a rhythm of feast and moderate famine that species have adapted to over evolutionary time. Off Peru, conditions are different. There, the southeast trade winds blow almost constantly throughout the year, maintaining more or less continuous upwelling. The result is one of the most productive marine ecosystems on Earth, year-round, never shutting down, always bringing nutrients to the surface. This constancy has made Peru one of the world's largest fishing nations despite its relatively small coastline. The Peruvian anchovy fishery alone, sustained almost entirely by upwelling, has at times accounted for more fish catch than all the freshwater and marine fisheries of North and South America combined. One country, one species of small fish, outweighing entire continents. That's the power of upwelling when it runs at full strength, when the ancient machinery operates without interruption. Around the world, there are 5 major coastal upwelling systems. 5 regions where the combination of wind, coastline orientation, and ocean circulation creates persistent zones of cold, nutrient-rich water rising to the surface. Each has its own character, its own seasonal patterns, its own ecological community, but all share the fundamental process of Ekman transport pushing surface water offshore and deep water rising to replace it. These 5 systems are scattered across different oceans, different hemispheres, but they're united by their extraordinary productivity and by their importance to human societies. They are the California Current System along the west coast of North America, the Humboldt Current System along the west coast of South America, the Benguela Current System along southwestern Africa, the Canary Current System along northwestern Africa, and the Somali Current System along the Horn of Africa. Together, these 5 systems produce roughly 25% of the world's total marine fish catch, harvested from only 5% of the ocean's surface. The concentration of productivity is almost incomprehensible, a testament to the power of upwelling to transform barren water into thriving ecosystem. The Humboldt Current System, also called the Peru Current, is the most productive of all. It flows northward along the coasts of Chile and Peru, carrying cold water from the Antarctic region toward the equator. Southeast trade winds blow parallel to the coast almost year-round. driving persistent upwelling. The water that rises comes from depths of 100 to 600 meters, emerging at temperatures as low as 15 or 16 degrees Celsius even in tropical latitudes. This cold water creates a narrow band of biological richness pressed against the South American coast, extending up to 1,000 kilometers offshore, but most intense within the first few hundred kilometers. The dominant fish species is the Peruvian anchoveta, a small silvery fish that feeds directly on the phytoplankton and zooplankton nourished by upwelling nutrients. Anchoveta schools can be enormous, stretching for kilometers, darkening the water with their numbers. These fish support not only a massive commercial fishery but also huge populations of seabirds, pelicans, cormorants and boobies that nest on rocky islands and cliffs along the coast. The birds feed so intensely on the anchoveta that their droppings, called guano, accumulate in thick layers on the nesting islands. This guano is so rich in nitrogen and phosphorus that it was once harvested as fertilizer and exported around the world, valuable enough that Peru fought a brief war in the 19th century, partly over control of guano-producing islands. The entire ecosystem, from microscopic phytoplankton to industrial fishing vessels, depends absolutely on upwelling. When El Niño events disrupt the upwelling cycle, the consequences cascade through every level. The anchoveta disappear or migrate, the birds starve by the millions, and the fishing industry grinds to a halt. The sudden absence reveals just how specialized and vulnerable this ecosystem is, how finely tuned to the constant delivery of nutrients from below. The California Current system extends from southern British Columbia down to Baja California, a span of roughly 4,000 kilometers. Like the Humboldt system, it's an eastern boundary current, meaning it flows generally equatorward along the eastern edge of an ocean basin. The upwelling season here is more variable, strongest in spring and summer when northwesterly winds blow steadily, weaker in winter when winds are lighter and more variable. The system is split into northern and southern subsystems, divided roughly at Point Conception in California, where the coastline bends sharply eastward. North of this point, upwelling is strong and consistent during the favorable season. South of it, upwelling is weaker and less predictable. The waters off Oregon, Washington, and Northern California turn intensely cold during summer upwelling events, sometimes dropping to 10 or 11 degrees Celsius, creating a shock for swimmers but ideal conditions for productivity. The cool water supports rich populations of krill, small shrimp-like crustaceans that form enormous swarms. These krill feed on the upwelling-fueled phytoplankton and zooplankton, and in turn support salmon, rockfish, seabirds and marine mammals including gray whales that migrate along this coast specifically to take advantage of the abundant food. The California Current system has been studied more intensively than perhaps any other upwelling region, with research vessels, satellites, autonomous underwater vehicles and moorings constantly monitoring the ocean state. Scientists have learned that even small changes in wind patterns or ocean temperature can have large effects on productivity and on the species that depend on upwelling-driven food webs. Recent research has also revealed that upwelling zones along this coast are becoming more acidic than the open ocean because the deep water being brought to the surface has accumulated carbon dioxide from decomposition, and this water is now also absorbing additional carbon dioxide from the atmosphere. The result is a double dose of acidification, natural and anthropogenic, that challenges marine organisms trying to build shells or skeletons. The Benguela Current system flows northward along the southwestern coast of Africa, from South Africa through Namibia and into Angola. It's divided into northern and southern subsystems, separated by an area of especially intense upwelling off Lüderitz, Namibia, which is considered the strongest upwelling zone in the entire world. Winds here blow with remarkable consistency, and the continental shelf is narrow, allowing upwelling to bring very deep water close to shore. The resulting productivity is staggering. The Benguela supports major fisheries for sardines, anchovies, and hake, as well as important populations of Cape fur seals, African penguins, and various seabirds. Like the Humboldt system, it once had islands covered in guano from seabird colonies, harvested commercially for fertilizer in the 19th and early 20th centuries. The Benguela system has experienced dramatic changes over recent decades, partly due to overfishing and partly due to natural climate variability. In some regions, sardine populations collapsed and were replaced by jellyfish blooms, a shift that has proven difficult to reverse. The northern Benguela in particular has undergone what scientists call a regime shift, a fundamental reorganization of the ecosystem into a new, less productive state. This serves as a warning about the fragility of upwelling systems when fishing pressure removes too many fish too quickly, disrupting the delicate balance between predators, prey, and the nutrient supply from below. Despite these challenges, the Benguela remains one of the world's most important upwelling regions, a center of marine productivity in an otherwise oligotrophic South Atlantic Ocean. The Canary Current system flows southward along the northwestern coast of Africa, from Morocco down to Senegal and beyond. It's influenced by the presence of the Canary Islands, which sit offshore in the middle of the current and affect its flow patterns. Upwelling along this coast is seasonal, strongest in summer when trade winds blow most consistently. The system supports important fisheries for sardines, mackerel, and other small pelagic fish, as well as more valuable species like octopus and grouper. The coastal waters of Morocco, Mauritania, and Senegal are among the most productive fishing grounds in the Atlantic, drawing fishing fleets from around the world. This has led to concerns about overfishing and about the fairness of fishing agreements that allow foreign vessels to harvest fish from these nutrient-rich waters. The productivity of the Canary Current system is somewhat lower than the Humboldt or Benguela systems, but still far higher than the open ocean. The upwelling supports not only commercial fisheries but also subsistence fishing by coastal communities that have relied on these waters for centuries. Recent studies suggest that upwelling intensity in some parts of this system may be changing due to climate shifts, with some regions showing increases and others showing decreases. The overall picture remains uncertain, but the potential for change adds another layer of complexity to managing fisheries and protecting the ecosystems that depend on upwelling. The Somali Current system is unique among the major upwelling regions because it's strongly seasonal, tied to the monsoon winds that reverse direction twice each year. During the southwest monsoon in summer, winds blow strongly from the southwest, parallel to the Somali and Arabian coasts, driving intense upwelling. The sea surface temperature can drop by 8 degrees Celsius or more within a few days as cold water wells up from depth. This creates a brief but intense bloom of productivity that supports fisheries and marine life throughout the region. During the northeast monsoon in winter, winds reverse, upwelling ceases, and the waters warm again. This on-off pattern creates a dramatic seasonal cycle that organisms must adapt to or migrate away from. The region also experiences upwelling along the coast of Oman during the summer monsoon. These Arabian Sea upwelling zones are important for regional fisheries and for supporting populations of whales, dolphins, and seabirds that time their presence to coincide with the upwelling season. The monsoon-driven nature of this system makes it particularly sensitive to climate variability. Changes in monsoon strength or timing could significantly alter the upwelling intensity and duration, with cascading effects throughout the ecosystem. Scientists studying the Somali Current have found evidence in sediment cores that upwelling intensity has varied over thousands of years in response to changes in monsoon patterns, suggesting that this system has always been dynamic and variable, responding to larger climate forces beyond the regional scale. Beyond these 5 major coastal systems, upwelling occurs in other contexts as well. Equatorial upwelling happens along the equator in the Pacific and Atlantic Oceans, where the trade winds blowing from east to west create a divergence of surface water just north and south of the equator. With surface water moving away in both directions, water from below rises to fill the gap. This upwelling is more diffuse than coastal upwelling, spread across a wider area, but it still creates a band of enhanced productivity across the tropical oceans, visible in satellite images as a thin green line following the equator. Upwelling also occurs around islands, seamounts, and other underwater features that deflect ocean currents. When a current encounters an obstacle, it's forced to flow around it, and in doing so can create zones of upwelling on the downstream side. The Galapagos Islands, for instance, sit in the path of equatorial currents and create local upwelling zones that enhance productivity around the islands, contributing to the unusual mix of cold water and warm water species found there. Even in the open ocean, far from coasts or islands, upwelling can occur in association with eddies, swirling currents that spin off from larger flows. Cyclonic eddies, rotating counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, tend to pump water upward in their centers, creating temporary oases of productivity in otherwise nutrient-poor waters. These eddies can persist for months, drifting slowly across the ocean, each one a small traveling upwelling system supporting its own miniature ecosystem. The water that rises during upwelling events doesn't arrive empty-handed. It carries with it the chemical legacy of everything that died and sank in the ocean above, decomposed by bacteria in the darkness below. The nutrients it brings are precisely what phytoplankton need to thrive, delivered in ratios that remarkably match almost exactly the ratios in which phytoplankton incorporate these elements into their cells. This match was first described by oceanographer Alfred Redfield in the early 20th century and is now called the Redfield ratio. On average, phytoplankton incorporate carbon, nitrogen, and phosphorus in a ratio of about 106 atoms of carbon to 16 atoms of nitrogen to 1 atom of phosphorus. And remarkably, when you measure the nutrients in deep ocean water, you find nitrate and phosphate in almost exactly a 16:1 ratio. This isn't coincidence. It's the result of millions of years of evolution and biogeochemical cycling. Phytoplankton have evolved to use nutrients in the proportions available in the ocean, and the ocean's nutrient ratios reflect what sinks from the productive surface. It's a feedback loop, perfectly balanced over time. When upwelling brings this nutrient-rich water to the surface, phytoplankton respond within hours. Cells that have been nutrient-starved begin dividing rapidly. Growth rates accelerate. Within a day or two, concentrations of phytoplankton can double. Within a week, the water can be transformed from relatively clear to opaque with life. The dominant phytoplankton in upwelling regions are usually diatoms, single-celled algae that build intricate shells from silica, the same material that makes up sand and glass. Diatoms are supremely efficient at converting sunlight and nutrients into new cells. They're also large by phytoplankton standards, typically 10 to 100 micrometers across, making them easy for zooplankton to capture and consume. This size and efficiency makes diatoms the preferred base of upwelling food webs. They grow fast, they're nutritious, and they can be eaten by organisms like copepods, small crustaceans that are themselves eaten by fish. The food chain in upwelling zones tends to be short and efficient, a straight line from diatoms to copepods to anchovies to predators. This directness is why upwelling zones are so productive at higher trophic levels. Less energy is lost at each step because there are fewer steps. Contrast this with the oligotrophic or nutrient-poor open ocean. There, the phytoplankton are dominated by tiny cyanobacteria and other picoplankton, cells so small that copepods can't eat them directly. Instead, these tiny cells are eaten by even tinier protists, which are eaten by somewhat larger protists, which might finally be large enough for copepods to consume. This is called the microbial loop, a complex web of interactions where energy is passed through many small hands before reaching anything substantial. At each transfer, energy is lost. By the time you reach fish-eating level, very little of the original photosynthetic production remains available. This is why the open ocean, despite covering most of the planet, is relatively unproductive from a fisheries perspective. The food webs are too long, too inefficient. Upwelling zones bypass this problem by supporting large phytoplankton that can be eaten directly by larger zooplankton, creating a short, efficient path from sunlight to fish. This efficiency, more than anything else, explains why upwelling zones produce so much fish from so little ocean surface area. The nutrients, the diatoms, the copepods, the anchovies, they're all part of a finely tuned system that has been optimized over millions of years to convert upwelling nutrients into biomass as quickly and efficiently as possible. The blooms that form in upwelling zones don't just feed fish, they also affect the chemistry of the water and even the atmosphere above. Diatoms and other phytoplankton remove carbon dioxide from seawater during photosynthesis, incorporating carbon into organic compounds. This draws down the concentration of dissolved COs in surface water, which in turn allows the ocean to absorb more CO from the atmosphere. Upwelling zones are therefore important carbon sinks, pulling atmospheric carbon dioxide into the ocean, and when phytoplankton die and sink, potentially sequestering that carbon in deep water or seafloor sediments for long periods. Some estimates suggest that upwelling zones, despite their small area, account for a disproportionate share of the ocean's total carbon uptake. However, this is complicated by the fact that the upwelling water itself brings dissolved COs up from depth, COs that was released by bacterial decomposition in the deep sea. So upwelling zones both emit and absorb carbon dioxide, and the net balance depends on the local conditions, the intensity of upwelling, the productivity of phytoplankton blooms, and many other factors. Recent research has shown that as atmospheric COs levels rise, the deep water being upwelled is becoming more acidic, carrying higher concentrations of dissolved carbon dioxide accumulated over decades. When this already acidic water reaches the surface and absorbs additional atmospheric CO2 slots, the seawater with pH levels significantly lower than the historical norm. This poses challenges for marine organisms that build shells or skeletons from calcium carbonate, including many species of phytoplankton, zooplankton, and shellfish. The famous oyster hatcheries along the Oregon coast have already experienced massive die-offs during upwelling events when the water became too acidic for oyster larvae to survive. Scientists are working to understand how upwelling ecosystems will respond to this increasing acidification, whether organisms can adapt, and what the consequences might be for the food webs and fisheries that depend on these systems. The timing of upwelling blooms can be critical for the survival of young fish and other animals. Many fish species have evolved to spawn at times when upwelling-fueled productivity will be at its peak, ensuring that their larvae hatch into a sea rich with food. Juvenile salmon entering the ocean from rivers along the California current, for instance, have much better survival rates when they enter during strong upwelling years with abundant zooplankton than during weak upwelling years when food is scarce. The same is true for seabirds. Species like common murres and Cassin's auklets time their breeding so that their chicks will hatch when upwelling has triggered zooplankton blooms, providing abundant food for the parent birds to catch and bring back to the nest. When upwelling is late or weak, chick survival plummets. The birds may not even attempt to breed, recognizing somehow that conditions aren't right. This tight coupling between upwelling productivity and reproduction means that changes in upwelling patterns can have rapid and dramatic effects on populations. If upwelling shifts in timing or intensity due to climate change, species will need to adjust their life cycles accordingly, and not all will be able to do so quickly enough. The risk of mismatch, where organisms arrive expecting food that isn't there, or where food arrives after the critical period has passed, is one of the major concerns scientists have about the future of upwelling ecosystems in a changing climate. The ancient synchrony between wind, nutrients, phytoplankton, and all the life that depends on them could be disrupted, with consequences we can only begin to imagine. The history of upwelling stretches back through geological time, though studying that history is challenging, because upwelling leaves only indirect traces in the sedimentary record. Unlike mountains or glaciers, upwelling doesn't carve visible features into the landscape, but it does affect what accumulates on the seafloor beneath upwelling zones. In regions where productivity is high year after year, century after century, the sediments become rich in organic matter, the remains of countless phytoplankton and other organisms that lived and died in the productive waters above. These organic rich sediments are sometimes called sapropels, and they can form thick layers that preserve a record of prolonged high productivity. By drilling cores into these sediments and analyzing their composition, scientists can reconstruct periods when upwelling was strong. Conversely, layers low in organic matter suggest times when upwelling was weak or absent. The sediments also contain the fossils of foraminifera, tiny shelled organisms that live in the water column. Different species of foraminifera prefer different temperature ranges and different nutrient conditions. By identifying which species are preserved in different layers of sediment, paleoceanographers can infer whether the waters above were cold and nutrient-rich, suggesting strong upwelling, or warm and nutrient-poor, suggesting weak upwelling. The shells of these foraminifera also preserve chemical signatures, ratios of different isotopes of oxygen and carbon, that record information about temperature and productivity. Magnesium to calcium ratios in the shells vary with water temperature, providing a thermometer that works across millions of years. By carefully analyzing these proxy records, scientists have reconstructed upwelling patterns extending back millions of years, through periods when Earth's climate was dramatically different from today. During glacial periods, for instance, when vast ice sheets covered much of North America and Europe, upwelling patterns were different from today. Sea level was lower. Continental shelves that are now underwater were exposed as dry land, and wind patterns were altered by the presence of ice sheets. Some upwelling zones weakened or shifted location. Others may have intensified. The exact changes varied from region to region, but the overall pattern is clear. Upwelling is not a static feature of the ocean. It responds to climate, to wind patterns, to ocean circulation, to the position of continents, to the configuration of ice sheets. Over geological time, upwelling zones have waxed and waned, shifted north or south, appeared and disappeared as the planetary climate system evolved. One particularly interesting period that scientists study is the mid-Pliocene, about 3 to 3.5 million years ago. During this time, Earth's continents were in essentially their modern positions, but the climate was warmer than today, with atmospheric CO levels similar to what we're experiencing now. By studying upwelling patterns during the mid-Pliocene, preserved in sediment cores, scientists hope to gain insights into how upwelling might respond to future warming. The evidence suggests that some upwelling zones were more intense during the mid-Pliocene, while others were weaker and the patterns were spatially complex. This historical record provides a kind of natural experiment, showing us what happened to upwelling during a period of warmth that may be analogous to our near future. The lessons are still being interpreted, but one thing is clear: upwelling is sensitive to climate conditions, and as climate changes, upwelling patterns change too. The ancient cycle of renewal is not unchanging. It adapts, shifts, responds to forces far larger than itself, and in doing so shapes the distribution of life in the ocean across deep time. Some of the world's most economically important geological resources owe their existence to ancient upwelling. Many oil and gas deposits formed in regions where upwelling once delivered high productivity over millions of years. The organic matter that accumulated in the sediments beneath these ancient upwelling zones was eventually buried, compressed and transformed by heat and pressure into petroleum. The richest petroleum basins in the world, including those along the west coast of Africa and in the Gulf of Mexico, were once sites of ancient upwelling or similar high-productivity environments. The same is true for phosphate deposits, rocks rich in phosphorus that are now mined for fertilizer. Many of these deposits formed in ancient upwelling zones where organic matter accumulated on the seafloor, and the phosphorus in that organic matter eventually became concentrated into layers of phosphate-rich rock called phosphorates. These rocks are now extracted and processed into fertilizer, completing a strange loop where nutrients that once drove ocean productivity millions of years ago are now spread on agricultural fields to drive productivity on land. The ocean's ancient bounty, preserved in stone, is harvested to feed the modern world. This connection between ancient upwelling and modern agriculture is rarely acknowledged, but it's profound. Much of the phosphate fertilizer used worldwide comes from deposits that formed in ancient seas, in regions where upwelling once brought nutrients to the surface with the same reliability and power that it does today off Peru or California. The cycle of nutrients from deep water to surface, from living organisms to sediment, from sediment to rock, and from rock back to life through mining and agriculture, spans millions of years and connects the ancient ocean to contemporary civilization in ways we rarely stop to consider. But there's a more immediate connection between ancient patterns and modern life, and that connection is disrupted regularly by one of the ocean's most powerful phenomena, El Niño. Every few years, on an irregular schedule that makes prediction difficult, the normal patterns of winds and ocean circulation in the tropical Pacific shift dramatically. The trade winds that usually blow strongly from east to west slacken or even reverse. Warm surface water that's normally piled up in the western Pacific sloshes back eastward towards South America. And when this warm water arrives off the coast of Peru and Ecuador, it spreads across the surface like a blanket, preventing cold water from upwelling. The thermocline, the boundary between warm surface water and cold deep water, deepens significantly. Even if winds blow in the right direction, even if Ekman Transport tries to push surface water offshore, the water that rises to replace it comes from above the thermocline now, from the warm nutrient-depleted layer. Upwelling may technically still occur, the water may still rise, but it brings nothing of value. No nutrients, no productivity, no food chain. The ecosystem collapses almost overnight. Anchoveta that have no plankton to eat swim away or die. Seabirds that find no fish abandon their nests, their chicks starving by the hundreds of thousands. Fishermen who depend on the anchoveta catch watch their nets come up empty. The entire productive machine grinds to a halt, not because the physical process of upwelling has stopped, but because the source water has changed. The engine is still running, but it's pumping empty water, water stripped of the nutrients that make upwelling meaningful. This is El Niño, named by Peruvian fishermen centuries ago who noticed that every few years, around Christmas time, warm water would appear and fish would vanish. They called it El Niño, the child, in reference to the Christ child and the Christmas timing. Now we know that El Niño is part of a larger phenomenon, the El Niño Southern Oscillation, or ENSO, a massive seesaw in the atmosphere and ocean that affects weather and climate around the world. The effects of El Niño on upwelling are most severe off Peru and Ecuador, but they ripple outward. The entire equatorial Pacific upwelling zone weakens during El Niño because the trade winds that normally drive it are diminished. Even upwelling zones far from the tropics can be affected through teleconnections, long-distance linkages in the atmosphere that transmit the influence of El Niño to distant regions. The California current may experience warmer water and reduced productivity during El Niño years, though the effects are generally less dramatic than off Peru. For coastal communities in Peru, El Niño can be devastating economically. The fishing industry, which employs thousands of people directly and supports many more indirectly, essentially shuts down. Government revenues from fishing licenses and fish exports plummet. Food supplies are disrupted. The 1972 El Niño, combined with overfishing, caused the Peruvian anchovy population to collapse so severely that the fishery didn't fully recover for over a decade. Catches that had reached 10 or even 12 million tons per year dropped to just a million or two. The economic and social consequences were enormous, rippling through Peruvian society for years. The 1982 through 1983 El Niño was one of the strongest on record, with catastrophic effects not only on upwelling but on weather patterns globally. Peru experienced torrential rains and flooding that destroyed infrastructure and crops. At the same time, Australia and Indonesia experienced severe drought. The disruption of upwelling off Peru was so complete that warm water fish species normally found only in tropical regions appeared along the coast, a sign of just how thoroughly the cold upwelling water had been replaced. Seabird populations crashed, fur seals and sea lions suffered high mortality. The ecosystem entered a state so different from normal that it seemed like a different ocean entirely. And then, after months, the winds shifted back, the warm water retreated westward, upwelling resumed, and productivity returned. But the recovery took time. Phytoplankton bloomed again quickly once nutrients returned, but it took longer for zooplankton populations to rebuild, longer still for fish to return, and years for seabird populations to recover through new breeding seasons. The more severe the El Niño, the longer and harder the recovery. The opposite phase of ENSO, La Niña, brings intensified upwelling. During La Niña events, trade winds blow more strongly than normal, pushing even more surface water westward and causing even stronger upwelling along the South American coast. The water that rises is colder than usual, sometimes extraordinarily cold, and loaded with nutrients. Productivity surges. Fish populations can explode during La Niña years, and fishery catches often reach their peaks. But La Niña can also bring its own problems. The water can be so cold and the upwelling so intense that oxygen levels in near-shore waters drop dangerously low, creating hypoxic conditions that stress or kill marine life. And for fisheries, a sudden abundance can lead to overfishing if catches are increased too aggressively, setting the stage for problems when conditions return to normal or swing toward El Niño again. The cycle of El Niño and La Niña, irregular as it is, has been operating for thousands of years. Evidence from coral cores, tree rings, ice cores, and sediment records shows that El Niño events occurred throughout the Holocene and probably long before. Marine organisms off Peru have evolved in an environment where upwelling is normally strong but periodically fails completely. This extreme variability has shaped their life histories, their reproductive strategies, their ability to disperse and find refuge. Some species have evolved to be generalists, able to feed on different prey depending on what's available. Others time their reproduction to avoid El Niño years if possible, though predicting El Niño far enough in advance to adjust breeding timing is beyond the capability of most species. The ecosystems have resilience built into them, an ability to bounce back after disruption, but that resilience has limits. If El Niño events become more frequent or more severe, or if they combine with other stressors like overfishing, pollution, or long-term warming, the ecosystems may not be able to recover fully between events. The ancient rhythm could be thrown off balance in ways that fundamentally alter these productive systems. Scientists are working hard to predict how upwelling will change as the global climate continues to warm. The question is enormously complex because upwelling depends on wind patterns, which in turn depend on temperature gradients between the ocean and land, between tropics and poles, between surface and atmosphere. As Earth warms, all of these temperature gradients are changing, but not uniformly. Some regions are warming faster than others. The poles are warming faster than the tropics, land is warming faster than ocean, the surface atmosphere is warming faster than the surface ocean in some places but not all. These differential warming rates affect wind patterns in ways that are difficult to predict with confidence. One hypothesis, proposed by oceanographer Andrew Barkun in 1990, suggests that as land warms faster than ocean, the temperature difference between them will increase. This stronger temperature gradient could drive stronger winds along coasts, leading to more intense upwelling. This is called the Barkun hypothesis, and it's supported by some observational data showing that winds have indeed intensified in some upwelling regions over recent decades. Satellite measurements of sea surface temperature show expanding cold tongues along some upwelling coasts, suggesting intensification. However, the picture is not uniform. Some upwelling regions show signs of intensification while others show signs of weakening or little change. The reasons for these regional differences are still being investigated, but they likely relate to how large-scale atmospheric circulation patterns are changing in response to warming. The Hadley cells, Walker circulation, jet streams, all these major features of atmospheric flow are shifting in complex ways that affect winds at regional scales. Computer models of future climate generally predict that upwelling will continue in the major systems, but with changes in intensity, timing, and spatial extent, some models suggest poleward shifts in upwelling zones as wind systems migrate toward the poles with warming. This could mean that upwelling intensifies in regions that are currently farther from the equator, while weakening in regions closer to the equator. Such shifts would have profound effects on ecosystems and fisheries that are precisely adapted to current upwelling locations. Fish populations might need to move poleward to follow the productivity, but coastlines and fishing ports don't move. Communities that have depended on upwelling fisheries for generations might find themselves stranded as the productive zones shift away. At the same time, regions that currently don't experience significant upwelling might become more productive. The overall global picture is one of redistribution rather than simple increase or decrease, a rearrangement of where upwelling occurs and how strong it is. But within that rearrangement, there will be winners and losers both ecologically and economically. Another major concern is the increasing stratification of the ocean. As the surface warms, the difference in density between warm surface water and cold deep water increases. This makes it harder for wind-driven processes to mix the two layers together. Stronger stratification means upwelling has to work harder to bring deep water to the surface, potentially reducing the amount of nutrients delivered even if wind strength remains the same or increases. Some studies suggest that this stratification effect could outweigh any intensification of winds, leading to a net decrease in nutrient supply to surface waters. The deep reservoir of nutrients would still be there, but the barrier preventing it from reaching the surface would be higher. This is particularly concerning for equatorial upwelling and for open ocean upwelling, which depend on weaker vertical mixing compared to coastal upwelling. The major coastal upwelling systems might be more resilient because winds there can be quite strong and the upwelling more direct, but even they could be affected if stratification becomes extreme enough. Ocean acidification adds another layer of complexity. As mentioned earlier, upwelled water already tends to be high in CO shoal because of the decomposition that occurs at depth. This makes upwelling zones naturally more acidic than average ocean waters. Now, as atmospheric CO shoal dies, the deep water is accumulating even more CO shoal before it upwells. And when it reaches the surface, it encounters an atmosphere with still more CO shoal dyes to absorb. The result is seawater in upwelling zones that is becoming acidic at a faster rate than almost anywhere else in the ocean. Studies off the California coast have found that during intense upwelling events, the pH of coastal waters can drop to levels not expected globally for decades. Organisms living in upwelling zones are therefore experiencing future ocean chemistry conditions right now. How they're responding is a major research question. Some organisms may have adaptations that allow them to cope with naturally variable and sometimes low pH, since upwelling zones have always been more acidic. These organisms might be more resilient to future acidification than organisms living in more stable open ocean conditions. On the other hand, The rate of change is unprecedented, faster than anything in the geological record except during mass extinction events. Even adapted organisms might be pushed beyond their limits. Experiments have shown that many calcifying plankton, including important species like pteropods, small swimming snails that are a major food source for fish, struggle to build shells in acidic water. If pteropod populations decline in upwelling zones, the effects could cascade up the food web to fish, seabirds, and marine mammals. Fisheries could suffer even if overall productivity remains high because key links in the food chain are weakened. Scientists are racing to understand these complex interactions, to identify which species are most vulnerable and which are most resilient, to predict how ecosystems might reorganize in response to the combined stresses of warming, changing upwelling, and acidification. Despite these concerns about the future, upwelling systems have shown remarkable resilience over time, bouncing back from El Niño events, recovering from periods of overfishing, adapting to natural climate variability that has occurred throughout their history. The organisms that live in these systems have evolved in an environment that is highly productive, but also highly variable, subject to sudden changes in temperature, nutrient availability, and oxygen levels. This variability has selected for species that can tolerate wide ranges of conditions, that can reproduce rapidly when conditions are good, that can disperse widely to find favorable areas when local conditions deteriorate. These traits may help upwelling ecosystems adapt to future changes, though the pace of current change may be too fast for adaptation to keep up. The key to protecting upwelling systems going forward will likely be reducing other stressors that we can control, like overfishing and pollution, to give these ecosystems the best chance of adapting to climate changes that we cannot easily control. If fish populations are healthy and diverse, if food webs are intact, if water quality is good, then upwelling ecosystems will be more resilient to the changes ahead. But if they're already stressed by human activities, if populations are depleted, if pollution has degraded habitats, then even small climate-driven changes in upwelling could push them past tipping points from which recovery may be very difficult. One aspect of upwelling that is less well known but ecologically crucial is its effect on oxygen levels in the water. Upwelling brings not only nutrients but also water that's low in dissolved oxygen. Deep ocean water, especially in upwelling zones, has had organic matter sinking into it for a long time. Bacteria decomposing that organic matter consume oxygen, and because the deep water is isolated from the atmosphere, the oxygen isn't replenished. In some upwelling zones, the deep water becomes so depleted in oxygen that it creates oxygen minimum zones, or OMZs, layers of water where oxygen concentrations drop to levels that most organisms cannot tolerate. Off Peru and Chile, the OMZs is particularly intense, with oxygen levels near zero between roughly 100 and 600 meters depth. This creates a sandwich structure in the water column where surface waters are oxygen-rich. The OMZs in the middle is nearly anoxic, and deeper water below the OMZ has more oxygen again. Most marine organisms cannot survive in the OMZ and avoid it entirely. Fish, squid, most crustaceans, they all stay above or below this layer, but some specialized organisms thrive there. Certain bacteria can use nitrate instead of oxygen for metabolism, a process called denitrification. Giant sulfur bacteria, some visible to the naked eye, form mats on the seafloor beneath the OMZ. These bacteria use nitrate to oxidize hydrogen sulfide, which seeps up from the sediments, creating strange whitish mats that can cover large areas of the seafloor. When upwelling is strong, water from the OMZ can be brought right to the surface, creating temporary zones of low oxygen near the coast. Fish and crabs suddenly find themselves in water they cannot breathe, and may suffocate if they can't escape quickly enough. Mass mortality events have been documented where thousands of fish and invertebrates wash up dead on beaches after particularly strong upwelling pulses brought OMZ water to the surface. These events are natural, part of the normal dynamics of the system, but they can be dramatic, and for the organisms involved, catastrophic. The OMZ itself is not static. Its thickness and intensity depend on how much organic matter rains down from above, and how much ventilation, or mixing with oxygenated water, occurs. During El Niño events, when productivity drops, less organic matter sinks, and the OMZ can shrink or become less severe. During La Niña events, when productivity surges, more organic matter sinks, decomposition increases, and the OMZ expands and intensifies. Over longer timescales, changes in ocean circulation can affect how well the deep water is ventilated, how much oxygen it starts with before upwelling occurs. There's concern that as the ocean warms and stratifies, ventilation of deep water will decrease, leading to expansion of OMZs globally. This is already being observed in some regions, where OMZs appear to be growing thicker and extending into shallower depths. For upwelling zones, this could mean that the water brought to the surface is even lower in oxygen than it is now, creating more frequent or more severe low oxygen events at the surface. Organisms that have evolved to cope with naturally variable oxygen might still be pushed beyond their tolerances if the OMZ intensifies too much. The ecological consequences are difficult to predict, but could include shifts in species distributions, with oxygen-tolerant species expanding and oxygen-sensitive species retreating, further reorganizing the structure of these ecosystems. The ancient balance between productivity and oxygen consumption, between upwelling bringing nutrients and upwelling bringing oxygen-depleted water, could be tipping toward more frequent anoxia, fundamentally changing the nature of upwelling zones in ways we're only beginning to understand. Yet despite all the challenges and uncertainties, upwelling remains one of the ocean's most reliable and ancient processes. For millions of years, since long before humans evolved, winds have blown along coastlines, surface water has been pushed aside, and deep water has risen to replace it. The cycle has continued through ice ages and warm periods, through mass extinctions and evolutionary radiations, through the rise and fall of countless species. Upwelling has shaped the distribution of marine life, concentrated nutrients into zones of extraordinary abundance, and sustained ecosystems that have lasted longer than empires, longer than species, longer than continents have held their current shapes. The nutrients cycling through upwelling systems have been recycled countless times, passing from photosynthesis to death, from sinking to upwelling, from growth to decay, and back again, an elemental dance that predates humanity and will almost certainly outlast us. Each atom of nitrogen, phosphorus, carbon that gets upwelled today has made this journey before, perhaps hundreds of times, perhaps thousands. It was once part of a diatom that bloomed in some ancient sea, then an anchovy, then a seabird's egg, then guano, then dissolved nutrients sinking back down. It rose with upwelling again and became a copod, then a sardine, then a shark, then marine snow falling through darkness. And now it rises again, ready to fuel another bloom, another generation, another link in the endless chain. There's something profound and humbling about this deep recycling, this refusal of the ocean to waste anything, this perpetual renewal that keeps life abundant, even in places where nutrients should long ago have been exhausted. The ancient indigenous peoples who lived along upwelling coasts understood, perhaps intuitively, that these waters were special. The abundance of fish and shellfish, the massive colonies of seabirds on offshore islands, the predictable return of marine mammals to feeding grounds, all of this spoke to a richness that couldn't be found everywhere. They developed cultures, economies, and spiritual practices around these productive zones, recognizing them as gifts, as sacred spaces where the ocean offered bounty. When Europeans arrived and began industrializing the fisheries, harvesting guano by the shipload, catching fish by the million tons, the focus shifted from gratitude to extraction, from sustainability to maximum yield. Some upwelling fisheries have been pushed to collapse by over-harvesting, Peruvian anchovies in the 1970s, Namibian sardines more recently. Others have been managed more carefully and remain productive. The lesson learned repeatedly but not always heeded is that upwelling creates abundance, but not infinite abundance. The productivity is real, the nutrient supply reliable, but it can be overpowered by fishing fleets equipped with modern technology and driven by global markets, demanding ever more fish. The balance between what upwelling provides and what humans take is delicate, requiring careful management, international cooperation, and a willingness to limit harvests even when more fish could technically be caught. It requires, in a sense, a return to something like the relationship indigenous peoples had with these systems, a relationship built on respect, reciprocity, and understanding that abundance is a gift that must not be squandered. As you rest tonight, perhaps drifting towards sleep, consider the vastness of what we've explored. The wind blowing over dark water, invisible but powerful, pushing surface water aside in obedience to forces we can name but barely comprehend. The Coriolis effect, a consequence of the Earth's spin deflecting moving water at perfect right angles. The Ekman transport, layers of ocean twisting deeper and deeper into a spiral. And then the rise, cold water climbing through darkness toward light, carrying its burden of nutrients, the chemical legacy of everything that lived and died above. The phytoplankton responding with explosive growth, turning clear water green, feeding zooplankton that feed fish that feed birds and seals and humans. The food webs cascading upward from microscopic cells to apex predators. The fisheries, the economies, the coastal communities all depending on this ancient process continuing as it always has. The disruptions, El Niño arriving to shut down upwelling, La Niña driving it to extremes. The oxygen minimum zones where life cannot exist but specialized bacteria thrive. The acidification threatening shell builders. The future uncertainties, warming, changing winds, shifting zones of productivity. And underneath it all, the deep time perspective. The millions of years of upwelling shaping ocean life, the sediments accumulating, the nutrients cycling endlessly, death feeding life in a pattern older than mountains. All of this happening right now, quietly, invisibly, across certain strips of coastline around the world. The ancient cycle of renewal, turning as it has always turned, adapting slowly to whatever changes the planet brings, resilient but not invulnerable, productive beyond measure, but not beyond the reach of human impact. It's a system of such complexity and elegance that we're still unraveling its secrets decades into intensive study. The researchers who dedicate their careers to understanding upwelling, sailing on research vessels into cold, productive waters, deploying instruments, collecting samples, analyzing data. They speak of it with something approaching reverence. They've seen the blooms from ships and satellites, watched phytoplankton concentrations explode in real time, measured the nutrients, tracked the fish, witnessed the seabirds wheeling in thousands over schools of anchovies that have gathered to feed on copepods, that have gathered to feed on diatoms that are blooming because nutrients have upwelled. They've seen the system work in all its intricate beauty, and they've also seen it fail during El Niño events, seen the empty water where abundance should be, understood viscerally how precarious the balance is. And they're working now to predict how it will change, how we can protect it, how we might manage our relationship with these systems to preserve their productivity into the future. It's difficult work, complicated by the ocean's natural variability, by gaps in historical data, by the complexity of coupled ocean-atmosphere systems, by the challenges of predicting how organisms will respond to changes they've never experienced before. But the work continues because the stakes are enormous. Billions of people depend on fish for protein. Coastal economies from Peru to Morocco depend on upwelling fisheries. Ecosystems that have evolved over millions of years hang in the balance. And there's something else, something less tangible but perhaps equally important. These upwelling systems, in their productivity and their vulnerability, in their ancient rhythms and their uncertain futures, teach us something about our relationship with the ocean, about humility, about limits, about the consequences of disruption. They're classrooms, if we're willing to learn, offering lessons about sustainability, about resilience, about the deep connections between physical processes and living communities, about how actions in one place ripple outward in ways we can't always predict. The nutrients rising in upwelling zones connect the deep sea to the surface, the past to the present, death to life, microscopic plants to massive whales. Everything is linked. Everything affects everything else. And we, watching from shore or from satellites or from research ships, are part of that web too, dependent on upwelling, whether we know it or not, connected to the ancient cycle even as we work to understand it. In the end, upwelling is simply water moving, driven by wind, guided by rotation, carrying dissolved minerals from darkness toward light. Nothing mystical about the physics, nothing magical about the chemistry. It's all explainable, quantifiable, modeled in computer simulations that run on supercomputers, and yet in its consequences, in the explosive growth of life it triggers, in the abundance it creates from what seems like nothing, there's something that feels miraculous nonetheless. From cold, dark, still water comes the foundation for ecosystems that support more life per unit area than tropical rainforests. From simple nutrients, nitrate and phosphate and silicate, come blooms of phytoplankton that can be seen from space, that turn the ocean from blue to green, that feed a cascade of life culminating in dolphins and whales and humans. The transformation is almost alchemical, base elements transmuted into living abundance through the catalysts of sunlight and time. It's happening right now, this moment, somewhere off the coast of Peru or California or Namibia. Phytoplankton cells are dividing, zooplankton are grazing, fish are schooling, birds are diving, fishermen are hauling nets, and all of it because wind blew across water and cold nutrient-rich water rose to meet the sun. The ancient cycle continuing, as it has for longer than we can truly comprehend, as it will for who knows how much longer, depending on what we do, depending on choices we make about climate and fishing, and protecting what we have. The sea's ancient cycle of renewal, both fragile and resilient, both generous and demanding, both understood and mysterious, rising and falling with the wind and the tides of time. And now, as your thoughts begin to soften, and your body grows heavier, sinking towards sleep, perhaps you can carry with you this image of cold water rising through darkness, climbing toward light, bringing with it the seeds of abundance, the promise of life renewed. The nutrients dispersing into sunlit water, the phytoplankton beginning to bloom, the ocean transforming from desert to garden in a matter of days, the food chains building upward, efficient and direct, each link depending on the one below, all depending ultimately on that cold water rising, on upwelling continuing its ancient work. It's been happening long before you existed. It's happening now while you rest, and with care and attention and a measure of luck, it will continue long after. The cycle of renewal, older than memory, steady as breath, the ocean's gift to life, offered freely wherever wind and current and coastline align to allow it. May you sleep well tonight, carried on gentle currents, knowing that somewhere the sea is upwelling, somewhere life is blooming, somewhere the ancient patterns continue their patient work. Good night, and thank you for journeying into the depths with me tonight. If you're still awake, the next voyage into ocean mysteries awaits whenever you're ready. Sleep softly, and dream of rising water carrying light.